Hi, welcome to Physics Teacher, the channel that prepares you for the Waterloo Math and Science Contest. This is a grade 12 physics or Isaac Newton contest question. And in it, we have Ryan's eyes 1.6 meters above the edge of a swimming pool. He looks directly across the 7-meter wide pool. Light from the bottom corner hits his eyes in such a direction that the apparent depth of the pool H is only 30 centimeters. If the index of refraction of water is 4/3, calculate the actual depth of the pool, capital H. Give it a try, and I'll be right back with the solution. Alright, so we're going to start this question by drawing some of these angles here. So what's actually happening is light is coming from this bottom corner here, reaching the barrier between water and air, and then refracting. In this case, since it's entering a medium that's less dense, going from water to air, it's refracting away from this normal. This normal is this red line here, which is perpendicular to the surface of that medium change between water and air. Now the angle that the light makes as it hits that boundary is called the angle of incidence, and the angle that it makes to the normal as it leaves that boundary is called the angle of refraction. Once again, since light is going from water into air, which is from a medium that is more dense into a medium that is less dense, that angle of refraction is going to be greater than the angle of incidence. And we're going to need to calculate some of these. Now, we know that the entire length of this pool is 7 meters. Let's call this length here, from the far edge to here, we'll call that x. And therefore, this length here is going to be 7 minus x. So we have two triangles here. We have this triangle, and we have this triangle here. Now, since this normal line is parallel to the edge of the pool, we can also say that this angle here is also the angle of refraction. That means this triangle and this triangle are similar triangles. So with similar triangles, what I can do is compare their lengths of their sides using a ratio. So I'm going to start by looking at this triangle. I'm going to take this side, which is 1.6. I'm going to divide that by this side of the same triangle, which is 7 minus x. And that is going to be equal to the exact same ratio of sides for this triangle here because they're similar. So this one is going to be small h, which is given as 0.3 meters divided by x. Alright, so I can cross multiply these. So I'm going to get 1.6x is equal to 0.3 all times by 7 minus x. And then I can distribute that 0.3 to give us 2.1 minus 0.3x. I'm going to bring that 0.3 to the other side of the equation, so I collect like terms, and it'll add to give 1.9x equals 2.1, or dividing both sides by 1.9 gives x to be 1.105. Now that I know what x is, and I also know what h is, I can calculate that angle of refraction using trig ratios. Since this is a right angle triangle, I can just say the tan, the angle of refraction, that is opposite over adjacent, or x over h, which would be 1.105 over h, which is 0.3, and take the inverse tan of both sides to get the angle of refraction as 74.81 degrees. Alright, moving on to step 2 then. Now that I know the angle of refraction, I'm going to use Snell's law to calculate the angle of incidence. Snell's law says that the index of refraction in our first medium times that sine of the angle of that first medium, which is our incident angle, is going to equal to the index of refraction of the second medium times the sine of the angle of refraction, or the angle to that normal through that second medium. Now N1 is going to be the index of refraction in water, which is given as 4/3 times the sine of the incident angle. Now in air, the index of refraction is very, very, very close to 1. Not exactly, but we are perfectly fine to approximate it as 1. So that's just going to be 1. And we're left with the sine of the angle of refraction, which we just calculated to be 74.81 degrees. So rearranging, we can figure out the incident angle as 3/4 times the sine of the refracted angle. And when we take the inverse sine of both sides, we get the incident angle to be 46.37 degrees. So this incident angle here is 46.37 degrees. Now what I'm trying to calculate is the height, which is right here. And what I've already calculated is this length, which is x. So I previously calculated x to be 1.105. And because this angle is extremely close to 45 degrees, I think we could probably take a pretty good guess that this angle here is going to be very close to x, probably just a little bit less, but let's calculate it anyway, since this is a right angle triangle. You can say the tan of theta I is going to be opposite, which is 1.105, divided by adjacent, which is the height, the actual height of the pool. So the actual height of the pool then is 1.105 divided by the tan of that incident angle, 46.37, which turns out to be 1.053 meters, or our answer is E.